There are many properties that will come in handy when it comes to evaluating integrals, and we'll study a few of them here. We're going to start off with a fairly simple sketch. The idea of the integral of cos of x. So cos of x has this shape here, and we're going out to negative pi over 3, which is, here's pi over 2, so pi over 3, negative pi over 3. When we write this integral down, we're asking for the heights of cos x times little units of x, little rectangles, and again that would add up to the area in between these two barriers here. So this area here is what is represented by the integral negative pi over 3 to pi over 3 with respect to x of cos of x. Now what if someone tells us that the integral from 0 to pi over 3 has a specific value? So if we block off this half of it, make it look a little more accurate here, we're told now that this interval here from 0 to pi over 3 has an area of root 3 over 2. Then what's the size of the area we sketched? Well, it's pretty clear that the integral over the whole entire interval from negative pi over 3 to 3, pi over 3, of cos of x, we can write it in two pieces. We just look at the areas and say, I'm going to divide it right down the middle here and talk about the integral from minus pi over 3 to 0. Okay, so highlight the contrast in the limits of integration. We're keeping the integrand the same. And what do we get here? We have 0 to pi over 3. So what have we done? We've simply taken the interval from negative pi over 3 to pi over 3 and broken it into two pieces, two segments, and written our integral in those two segments. And the reason we might want to do that is that we know this now is root 3 over 2, and by symmetry, cosine is exactly the same shape on the other side. We can immediately infer that this is also equal to root 3 over 2. So the overall area is made up of one area, which we know, and another area that's a copy of it. And so we're going to get an integral of root 3 over 2 plus root 3 over 2. And that, of course, will be 2 root 3's over 2, or simply root 3. So what we're doing here is taking advantage of one of the properties of integrals, that we can break up an interval if we like and evaluate the whole area on separate intervals if that's easier for us. Here it is written out more formally. The integral from a to b of a function with respect to x. It can be the same as the integral from a to b, put squares around these ones. So the starting point's the same, the end point's the same, and then we insert a breakpoint somewhere in the middle, which is going to help us or allow us to break this long integral into two smaller ones. And so very much like we just sketched in the last example, if we had the integral from a to b of some function, that's this region here, or we can divide that interval into pieces, an a and a b, and let's put c. It doesn't have to be in the middle. So we'd have this curve, that would be the one integral, and then we would continue on and find this integral. Take the whole thing or break it into pieces if we like. Perhaps a less intuitive property that sometimes comes in handy but is less frequently used than the last one is that if we swap the limits of integration, a to b, and change it to b up to a, then we get a negative sign out front. We can illustrate a simple example of this property by looking at the integral from 0 to pi over 3 plus the integral, seems odd, but from pi over 3 to 0. Our temptation might be to say these things don't matter, but if we look at how we did this integration before, we'll simply sketch it out here as the limits. We have the opposite case of the last time. Here we have two intervals and the middle points match, so we can simplify that down to the integral from 0 to 0 of cos of x dx. And if that's the case, think of what that means in terms of area. We have the graph of cos of x, and we're asked for the area between x equals 0 and x equals 0. That, I think we can all agree, is a big 0. There is no area there because there's no width, no interval. And if that's 0, then the only way for that to work is for one of these two things to be negative. We know that the area underneath 0 to pi over 3 is perfectly reasonable. It's a nice positive value. So this must somehow cancel it out perfectly, and the way for that to work is it'll be the integral from 0 to pi over 3. If I reverse these two things, then we add a negative as well. We're going to get negative the integral from 0 to pi over 3. And of course, if I take something minus itself, we get 0 as well. Again, it doesn't happen often, but it does happen often enough that we end up with strange limits where they're not perhaps in the natural order we would like. If we flip the order, all we have to do is take that into account with a negative sign out front. It's also not too hard to give a Riemann sum. Remember the sums of f's times delta x's for this property here. If we're integrating from a up to b, then our delta x's are positive. We're taking little segments, adding them, and each segment is directed from left to right. However, if we go the other direction, and this is our integral from b to a, we're implicitly heading down this way, well then each step that we take is a little delta x. Our little delta x's would be negative, and so if we want to swap those two things, remember we've got a dx here and a dx here. To go between these two versions, we'd have to multiply by -1. And that's going to flip the sign of the delta x's, is what we're really doing when we switch the signs, or the order rather, of the limits of integration.